This tutorial introduces the Steel Connections tab in ideCAD Structural. It begins with fast mode for automatic connection generation and continues with manual detailing of base plates, bolts, anchors, and welds. Moment and shear connections are applied to beam-to-column joints, while haunches, stiffeners, and splices enhance structural capacity. Secondary beam, purlin, bracing, crane, and wind load connections are also adjusted. The workflow concludes with using favorites for fast application and final design checks. Now, let's move on to the connections. In this project, we will model several different types of connections and go over their key properties. At the top ribbon, you can see the Connections tab. I clicked on it once. The panel opens, and you can see the different connection types. There are two main categories clearly separated by a thick line. The first group is labeled connections and contains fully designed joints, including both pinned and moment-resisting connections. It also includes splice connections, brace connections, and steel column-to-base connections. These connections are designed according to American standards, specifically AISC 360-16 ASD and LRFD, and when applicable, AISC design guides and AISC 341-16. Detailed design reports are automatically generated based on these codes. The second group is labeled experimental. This section includes various connection types used for detailing purposes, but without design calculations. You will still find pinned and moment-resisting connections, as well as stiffening options, in this category. All the way to the right, you'll see the Draw and Fast Mode option. When I click on it, you'll notice it is highlighted to show it's active. This mode allows you to rapidly assign multiple connections without exiting the command. The software automatically detects the closest element or node your mouse is hovering over and places the connection accordingly. We recommend using this mode with caution when you're new to the software. The reason is simple. Since the command is sensitive to mouse position, you might accidentally place a beam-to-beam connection when you intended to model a column-to-beam connection. This can lead to unintended variations in your analytical model. Later on, we will also demonstrate how to model connections using fast mode efficiently. For now, let's start with shear connections. I navigated to the single plate connection option. There's a small arrow on the bottom right of the icon. I clicked it once to open the toolbar, where we can access detailed settings for this connection type. Here, you can see various types of shear connections that are fully designed. The same logic applies to moment connections as well. The list continues with brace connections and column-to-base connections. For example, I clicked once on the column-base connection. A long toolbar appeared, displaying the available subtypes of connections as icons. While the fast mode is still active, let's demonstrate it directly at the bottom of a column. I moved the cursor close to the bottom end of the column, and the connection was automatically created. Now, let's undo the operation. I double-clicked on the defined connection to open its properties. The first section is for primary direction stiffeners, where you can select different stiffener arrangements for the major axis. Just below that, you will see options for secondary direction stiffeners. When we move to the Plates and Grout tab, we can adjust key parameters such as plate thickness, height, and width. Additionally, you can modify grout settings, fitting plate, and cast plate dimensions. For now, I'll deactivate the grout option. Furthermore, you can easily follow what each parameter represents by referring to the diagrams displayed on this screen. Moving on to the Anchorage tab, you need to define the number of anchors in both the primary and secondary directions. Since we are modeling a moment-resisting base connection, I kept 3 anchors active in both directions. An important note: if you model the anchors within the flange width of the column section, the software automatically converts the connection to pinned internally, adjusting the degrees of freedom accordingly. You can visually confirm this in the Analysis Model view. For this example, I changed the anchor bolt diameter from M16 to M24. Since the spacing between the bolts is still sufficient, I didn't modify the other parameters. Let's take a look at the bolt settings. I clicked on the bolt properties section, and a new window appeared. The normal hole type is selected by default. There are 3 options available: normal, oversized, and custom. When you select custom, the corresponding input fields become active for further adjustments. I'll leave it on normal. On the right side, you can also choose between short slotted, long slotted, and custom slotted hole types. Regarding bolt diameter, you can select from a full range starting from M10 to M36. For bolt grade, as we selected ISO standards when setting up the project, the options range from ISO 4.6 to ISO 12.9. Just to clarify, since we initially selected European sections, the American bolt standards are not visible here. However, if you switch to American sections, all relevant American bolt types and grades will also be available. I clicked OK. Here, for both the primary and secondary directions, you can define the number of anchors and the spacing between anchors, where spacing refers to the distance between the centers of 2 adjacent bolt holes. Moving down to the anchor section, you will find different types of anchor options. You should select the anchor type that is appropriate for your project requirements. Additionally, the L1 and L2 parameters, which define anchor positioning, must be entered accordingly. In the chamfers section, you can define trimming operations on the edges of stiffener plates to prevent clashes or interferences within the joint geometry. Switching to the weld section, you will see numbered references corresponding to each weld in the visual diagrams, making it easy to identify each welding position. Once you click on any input box, you can right-click while your cursor is on the box to change the unit and enter your desired value. You will see all standard weld types as defined by AISC, including fillet weld, complete joint penetration, CJP, partial joint penetration, PJP, and other standard weld symbols. You can select the appropriate weld type from this screen. By default, welding is considered for shop fabrication drawings. Welded elements are grouped as assemblies and fabricated in the workshop. However, if welding is required to be performed on-site, you should activate the Site Weld option by ticking the checkbox on the right. Next, in the Weld Electrode section, the currently selected electrode has a yield strength of 480 N/mm superscript 2. If you wish to add a new electrode, click on Create New, then click on the New button in the pop-up window, where you can define the new electrode strength. For example, let's enter 510 N/mm superscript 2 and also assign it a custom name. This allows you to easily switch between electrode materials depending on your project requirements. Adding a new weld electrode is straightforward. As a side note, the A parameter, which defines the weld thickness, is shown in the visual diagrams within the weld menu. In the connection design reports, the software checks the W parameter, which represents the minimum weld thickness and is used for the calculation of its capacity. Keep this in mind during the design verification process. Lastly, in the Design Data section, you can select the material type of the base plate. Currently, the material is set to S235, but you can easily select a different material if necessary. open the design report. A notification appeared because I have not yet defined any foundation elements or concrete pedestals beneath the steel columns in this project. According to the connection design criteria, the concrete compressive strength of the reinforced concrete member supporting the base plate must be considered in the design checks. When no such concrete element is modeled, the software automatically assigns the properties of C25 grade concrete by default. I haven't performed any structural analysis, I simply opened the design report to showcase the structure. In the report window, the first section contains geometrical checks, followed by strength verifications. Looking closely, you can see clear references to bolt spacing, edge distances, both vertical and horizontal, and weld size, with each verification linked to specific code clauses and all relevant design parameters listed. Further down, you'll see strength verifications like base plate thickness check, bearing strength on concrete, and other limit states. After the analysis is completed, additional verifications might appear depending on the internal force effects acting on the connected members, while some checks may be omitted if irrelevant. At the bottom of the report, there's a summary of internal forces along with the critical load combination producing the most unfavorable effects. Since no analysis has been run, the fields for moment, shear force, and axial force are currently empty. I clicked OK to close the report. If you intend to apply this connection across multiple locations or throughout the project, you can use the favorites feature for efficient modeling. I saved this connection to favorites by assigning a name and clicking OK. Switching to fast mode, I quickly applied the base plate connection to all columns. Just hover your mouse over the bottom flange of each column and click once. As I mentioned earlier, the software automatically identifies the location of your cursor and places the connection accordingly. This makes it remarkably efficient to model repetitive details. And I've already completed the base plate modeling. Next, to simplify the model view, I'll use the filter tool. I'd also like to demonstrate both moment connections and simple shear connections. Let's start with a moment connection aligned along the major axis. For example, on intermediate floors, we can model a 4 bolts end plate moment connection. I'll disable fast mode to show you how to model in manual mode. For beam to column connections, you always select the column first and then the beam. The connection is placed accordingly. I want to point out something important here. All pre-configured connections in the software, whether moment resisting or shear connections, follow capacity design principles by default. For shear connections, parameters such as plate thickness, plate width and height, bolt quantity, and weld size are determined based on the shear capacity of the supported member. In the case of moment-resisting connections, both the column and beam cross-sectional properties are considered, with all connection details designed according to capacity design principles. One important note, specific seismic detailing requirements, such as cross-sectional limits stated in seismic codes, are not enforced during connection generation. These requirements must be checked from the design reports after analysis. If any insufficiency is identified in the connection design report after running the analysis, it is solely the engineer's responsibility to address and resolve it by modifying the structural design. The purpose of this feature is to ensure the generated connections are adequately safe under the anticipated design loads. However, you are always free to adjust or reduce the connection capacity if necessary for your project-specific requirements. Now, let's review the connection properties. In this section, we can adjust parameters such as plate thickness, plate width, and plate height. When I open the Bolts tab, I can define the horizontal spacing and vertical spacing between bolts. Below, V1 and V2 refer to the distances between the top flange and bottom flange of the beam and the bolt centroid. Further down, we have access to bolt properties. By clicking on this section, the bolt specification window opens, allowing you to choose between different bolt diameters, bolt grades, and hole types in line with design requirements. I confirmed my selections by clicking OK. Next, you'll notice a checkbox labeled Workshop Bolt. When this box is activated, it indicates that the bolted connection is to be assembled in the fabrication shop, meaning it will be pre-assembled and delivered to the site as a prefabricated unit. If the box remains unchecked, the software automatically considers the bolts as field bolts, meaning they are installed on-site during erection. The steel detail drawings will reflect this distinction by assigning workshop bolts and field bolts accordingly, including proper welding and assembly notes. By default, the workshop bolt option is unchecked since most connections, especially in structural steel erection, are typically field assembled. Additionally, the stiffener plate thicknesses are automatically determined by the software according to the flange thickness of the beam section to ensure proper compatibility and load transfer. When the beam is inclined, selecting the horizontal option automatically places the appropriate stiffeners aligned to the beam's horizontal axis. Next, let's move to the Extra Plates tab. I checked the box to activate it, and as you can see, a column web stiffener plate has been modeled within the column beam panel zone. This type of stiffener may be required, especially when seismic code requirements are involved, so it should be activated from this menu when necessary. In this example, I don't need it, so I'll deactivate it for now. Moving on to the next tab, we see the chamfers menu. By the way, if you double-click on the connection preview image, it will expand to full screen. Clicking again will minimize it back to normal view. The Welds tab works similarly. Each weld is numbered, and the illustration clearly shows which weld number corresponds to each location. For instance, weld number 4 is, by default, a complete joint penetration, CJP, groove weld, as required by the connection type. The remaining welds are fillet welds, and you can view and adjust their thickness in this tab. In the Design tab, you can define the material of the main connection plate. There are also options to add this connection to favorites and to generate a design report. The design report summarizes the geometric properties and the required design parameters. It begins with an overview showing the material grade, beam and column section properties, and the plate thickness, width, and height. Further down, you'll find geometric checks followed by strength checks. For each strength check, the report references the relevant design code clauses and provides detailed explanations for every parameter involved. Since I haven't run a structural analysis yet, there are no load combinations or internal forces shown at the bottom of the report. We'll review these details later in the design section after analysis is completed. For now, I'll continue with connection modeling. Now, for this corner region, I'll model the haunch connection. I'll select the column first, followed by the beam. Here, we have a similar connection geometry displayed, which offers two subtypes, bolted and welded configurations. You can easily switch between these options within this interface. I have selected the bolted option. As we adjust the parameters, the preview window on the side dynamically updates to reflect these changes. I have deactivated the bolt plates for this example. The bolt settings are similar to other connections, although there may be minor differences depending on the specific geometry of each connection. For extra verification, you can always monitor the connection configuration in the live preview window. The visuals within the Bolt tab clearly indicate which parameter corresponds to which geometric location, making it easy to make accurate adjustments. Under the Extra Plate tab, I set the stiffener plate length to 0 to effectively disable it. Because we changed the length of the cap plate attached to the beam flange to 0, I'm updating the cap plate bolts to 0 as well. This connection type is not designed according to AISC, which is why there is no Design Report tab available. Now, I activated Fast Mode. The software detects the closest connection point based on the cursor's location, whether it is near the I or J end of the beam, and identifies nearby elements, including beams, columns, and braces. That's why I'm moving the cursor close to the columns to automatically assign eaves haunch connections at all column beam intersections along the roofline. As you can see, it is essential to be careful while using this method since the software is sensitive to cursor proximity. Let's quickly check if there are any areas where connections have not been assigned yet. I'll repeat the same process in this region to ensure full coverage. Now, let's move on to review connections along the minor axis. To avoid clashes, I will first deactivate the stiffener plates in the 4-bolt end plate connection. Next, I selected a quad stiffener plate connection. I clicked the column first, followed by the beam. The connection was generated, and as you can see, the software automatically optimized the welding and geometric details of the brace connection to eliminate any clashes. Let's connect the column and the beam using a T-plate connection to complete all connections at the joint. As you can see, the software automatically recognizes the intersecting plates and creates the appropriate welds, ensuring there are no clashes. Let's modify the bracing configuration to apply an X-brace every 2 floors. I switched this brace to a V-brace so we can observe how the software handles multiple intersecting connections within a single joint. As shown on the screen, the software automatically adjusted the connections, welding details, and stiffeners around the node without any clashes, ensuring smooth and proper connections. This capability allows us to perform pre-detailing clash checks very efficiently. Using this workflow, we can complete clash detection checks in a very short time before proceeding with final steel detailing. For the sake of repetition, I have once again assigned the quad stiffener plate connection, selecting the column first and then the beam. I confirmed the selection by clicking OK. Next, I selected the T-profile connection, and similarly, clicked the column first, then the beam, and completed the operation. In this way, you can efficiently and interactively model column-to-beam connections along the minor axis. Another key convenience in connection modeling, something we already observed during element modeling, is that the software automatically generates connections for purlins, ties, secondary beams, and braces. This also applies to truss members, which we will explore in detail later. Of course, you can always change both the connection types and their parameters according to your design requirements. Now, looking at the secondary beams, I see that they have been modeled using a T-profile connection. There are also double angle, single angle, and single plate options available. Let's say, for example, we want to switch to a single plate connection. However, I noticed that the web depth of the primary beams is insufficient. Let's increase the section size first. I selected one of the beams, used the Select Similar command, chose Section, and switched to an IPE 270 section to update the beam sizes. Returning to the connections, as I mentioned earlier, the shear connections come with default settings that comply with capacity design principles. This means that the plate thickness, width, height, bolt diameter, bolt type, and weld thickness are determined to match the load carrying capacity of the secondary beam's cross-section. Let's open the design report and take a closer look. As usual, the report first summarizes the element properties, followed by the geometric and material properties of the connection. Since the analysis has already been run, we can see the analysis results at the connection nodes for the secondary beams, including the most critical load combination and the resulting internal forces from this combination. I clicked OK to exit. You can freely modify the plate orientation, thickness, height, and width. If you leave notch settings on automatic, the software automatically trims the secondary beam flanges to avoid any clashes. Weld thickness, electrode strength, and material selection continue under the following tabs, as we have seen before. Now, as you can see, we can change the connection types of secondary beams in one step by using the secondary beam command. In case you encounter any design inadequacy for these connections and need to modify them, here's what you should do. While holding down the Control key, when I select one of them, you can see that all of them are highlighted in purple. Let's also check this in the perspective view. Notice that it only selects the connections within this group and does not select the secondary beam connections on the upper story. By pressing Ctrl+E, you can open the Properties window and make the necessary adjustments. Next, let's check the purlins and their connections. First, I'll change the connection type. Again, while holding down Control, I selected one purlin connection, and it selected all of them in the group. I pressed Ctrl+E and opened the Properties window. I'd like to use a different connection type. After that, you can choose the desired connection option, such as bolt or weld connections to the main beam or bolt or weld connections to the purlin. In the Profiles section, you can either select this section from the drop-down list or access the section library by clicking Load Section. After making the adjustments, I'll repeat the same process for this other purlin group, which hasn't been modified yet. I clicked on one purlin connection, selected Purlin connection, and then used Ctrl+click to select the rest. By applying a saved favorite connection, I quickly completed the modeling process. Now, I'll show an example of a splice connection and move on to the crane connections. I selected the joining plates connection, picked the two beams one after the other, and it automatically applied the default configuration. Of course, I'll make some modifications to properly adjust the connection according to the project requirements. If you prefer, you can also add additional stiffener plates to the bottom area. For now, I will skip that step. This was what I meant by the fast mode. Depending on the mouse position, the software may automatically generate a connection between two unintended members. To avoid this, I'm switching to classic mode for more controlled data input. Additionally, we can use the seating support connection to connect curved beams to the relevant columns. I selected the seating support connection, and you can see various subtypes available. I chose a moment-resisting configuration. Let's also briefly cover crane and wind bracing connections. I had already placed a wind bracing connection earlier, but didn't explain it in detail at the time. Generally, the structure of all connections is quite similar. When using classic mode, the bottom toolbar will assist you, and you need to first select the primary member and then the secondary member. The connection properties typically consist of submenus for bolts, welds, main plate, chamfers, stiffeners, extra plates and material selection. As for the crane connection, the software automatically detects the first and last crane girders and places crane stoppers accordingly. For intermediate positions, you should select both crane girders to generate the connection properly. Now, let's quickly review one of the wind bracing connections I placed earlier. I selected the column first, then the beam. As you can see, the wind connection automatically adjusted the distance between the column and the beam. Trim and extend operations can be executed automatically through the connection definitions. I'll also discuss the bracing connections. As you know, bracing connections are automatically generated along with the bracing members, but you can always access and modify their properties afterward. I added stiffeners to the connection as part of the adjustments. Additionally, we can follow the same process for vertical bracing connections, which I'll demonstrate shortly. With that, we will complete the connection modeling process. As you can see, we've managed to model the majority of the connections in a relatively short amount of time. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.